Hello, people, and welcome back to another session. In this session, we'll be looking at the types of errors that we commit in hypothesis testing and their significance in one-way ANOVA. So, in hypothesis testing, there is a probability of committing two different types of errors, the type 1 error and the type 2 error. Let us define what these two types of errors are. So, the type 1 error is committed when you are rejecting the null hypothesis, but actually the null hypothesis is true. So these errors are also referred to as the false positive scenarios. When your null hypothesis is actually true, but you have ended up in rejecting the null hypothesis. Now, clearly, this particular error depends on the significance level of the test. And because this is so heavily dependent on the significance level of the test, we take our significance level or the alpha level extremely low to make sure that the probability of committing this error actually decreases. It also reiterates why we need to always have less significant, abysmally small significant values when we are going for hypothesis testing, and also why p values are so important when it comes to determining the result of hypothesis testing. The second type of error that we can commit is type 2 error. Now, type 2 error is the exact opposite of type 1 error. Basically, when you have failed to reject your null hypothesis, when actually your null hypothesis should have been rejected. Unlike type 1 error, which depends on the significance level or the alpha level, the type 2 error, also referred to as false negatives, it depends on the sample size. If in any instance you observe your calculation is such that you are committing type 2 error again and again, what you can do is just increase the sample size. Now, this type 2 error is also called power of the test. It is an extremely important error because it reiterates a very fundamental concept that we have studied earlier. Now, in the early parts of our discussion on hypothesis testing, I told you that when we are not able to reject null hypotheses, we always say that we have failed to reject our null hypotheses. We never say that I accept the null hypothesis. The reason is this: you do not know when you fail to reject the null hypothesis whether you have failed to reject it because the hypothesis is actually true, or you don't have enough power to reject the null hypothesis. Let me reiterate. When it comes to failing to reject null hypotheses, in any circumstance or in any situation, you cannot say with 100% certainty that you have failed to reject the null hypothesis because the null hypothesis is actually true. The alternate scenario would be that you do not have enough power to reject your null hypothesis, which means the sample size might cause the test to come up with a conclusion where you have failed to reject the null hypothesis. It does not mean, however, with 100% certainty that my null hypothesis is true. Therefore, we always say we failed to reject the null hypothesis. Now, we studied in the previous session in pairwise t-test that when we are finding out which pair of groups are different from one another, we use pairwise t-test for each of the two groups. So, from a very mathematical standpoint, let us suppose I have k different groups. My number of comparisons will be k into k minus 1 divided by 2. These are going to be my total number of comparisons. Now, let us suppose that the probability of committing a type 1 error for a single comparison is alpha. Let me repeat, the probability of committing a type 1 error for only one comparison is alpha. Then for total number of comparisons, what will be the amount of probability of committing a type 1 error? It will be alpha times C. This is the probability of committing type 1 errors across all pairwise tests. So you can see that there is a direct relationship or a direct proportional relationship between the number of comparisons and the probability of committing a type 1 error. The more the number of pairwise comparisons, the more the chances of committing type 1 errors. Therefore, it is very important that we limit the probability of committing a type 1 error. And the way we limit this high probability of committing a type 1 error is to actually change the significance level for each test. If my overall significance level is alpha, I have to make sure that for each of the comparisons, I take a much lower alpha value to make the rejection of null hypothesis more difficult. This is the central idea. So rather than having alpha as the significance level for all pairwise t-test, I'll have a new alpha called alpha star. And this alpha star will be nothing but original alpha divided by C. Where C is the number of comparisons, the number of comparisons, which is k into k minus 1 by 2. This right here. So instead of doing your pairwise comparisons at alpha significance level, you will be doing all pairwise comparisons at alpha star significance level. And this forms your crux for Bonferroni adjustment. So basically, Bonferroni adjustment is one of the simplest and most commonly used principle for multiple comparison procedure. So what Bonferroni adjustment does is it basically changes your significance level in such a way that the ability to reject your null hypothesis becomes a little more difficult than at alpha significance level. And we do that, remember, in order to make sure that our probability of committing type 1 error does not increase significantly. So Bonferroni is one type of adjustment that is done. Tukey adjustment is another type of adjustment for controlling the type 1 error. Tukey has more statistical power than Bonferroni. Now let us go back to R. In the previous session, I told you that there is a p-adjust method in one of the arguments for pairwise t-test. This p-adjust method can take values Bonferroni, and for Tukey, you can directly pass your ANOVA model. So for Bonferroni, if I pass, look at the changed value, the changed p-values. If you compare it from your previous scenario where your adjustment value was none, all the p-values have significantly increased. And now, difference between current heavy smoker and former smoker, the margins of distinction have become extremely minimal after Bonferroni adjustment. So this is what Bonferroni adjustment did. It actually increased my p-values to make rejection of null hypotheses all the more difficult to avoid type 1 error. Similarly, I do the same for Tukey. Now with Tukey, it represents my result in a different way. It shows my lower and upper value of confidence interval for each of the groups, and it gives me the adjusted p-values. And accordingly, we can make the comparison. Now, before I end the session, a very minute observation. If you compare your p-values of comparison, your p-values of comparison when your adjusted method was none to when the adjusted method became Bonferroni, you will see an increase in the p-value by a factor of C. Now, in this case, how many groups were there? You had heavy smoker, light smoker, former smoker, and never smoker. So 4 groups. Now I go back to my WordPad and I say, because there are 4 groups, my C is going to be 4 into 3 by 2, which is nothing but equal to 6. If I multiply 0.081 by 6, I get somewhere around 0.486, which is what I get here. So in Bonferroni adjustment, my p-values for each individual comparison, they increase by a factor of C, where C is the number of comparisons, which is equal to K into K minus 1 by 2, where K is the number of groups. So this brings us to the end of today's session. I'll see you all in the next session. Thank you so much.